Today we're going to add and subtract radicals. Before we add or subtract radicals, we have to make sure that we have like radicals. Radicals with the same index and the same radicand are like radicals. It is important to note that the square root of a plus or minus the square root of b is not the same as adding and subtracting b under one radical sign. So we cannot join different bases of radicals under one radical sign. That is exclusive for factors when we're multiplying. So this is a completely different process. So we must simplify each term individually, then add or subtract if they happen to be like radicands. So the steps we're going to follow today are to simplify each radical, identify like radicals. Finally, we can add or subtract the like radicals by adding or subtracting their coefficients or any variables that happen to clear the radical sign. For our first example today, we have the square root of 27 minus the square root of 25. So it's important that we work with each of these radical terms separately, and then we'll see if we indeed can subtract them. So we'll work with the square root of 27 first. You might already know that it comes from 9 times 3. I like to write the perfect square factor first because then it's in the proper order for us to simplify and have it in standard form. So try to get in the habit of breaking apart numbers with the perfect square first. Square root of 9 we know is 3, and 3 would remain under the radical for that other factor. Now we'll work with 75. If you don't remember what some of the factors of 75 are, it's okay. You're just going to go ahead and build yourself that factor ladder and you can create it. It ends with 5, so I'll divide by 5, and that would leave me 1, and that would leave me 5 goes into 25 5 times. Dividing 15 by 5, I have 3. Dividing 3 by 3, we end up with 1. So we see that really the factors are square root 25 and square root of 3. So I'll just move all this down so we have plenty of room. 3 square roots of 3 are for the square root of 27. And we just found that 75 breaks apart as 25 times 3. So with 25 under the square root times square root 3, simplifying, that makes 5 square roots of 3. So what we're subtracting is 5 square roots of 3. Now, do you notice anything special about the terms we ended up with? Both of these terms have square root of 3, and that's called a common radicand. So the way we continue the problem is we take the terms that have cleared the radical and combine those, 3 minus 5, and that will be multiplied by this common radicand, square root of 3. So 3 take away 5 leaves negative 2 square roots of 3. And that's our final answer. It somewhat looks like a form of factoring, doesn't it? Like greatest common factor. Now our next problem, in example 2, has 3 different terms, so we need to break those apart. With the square root of 32, I'll just work over here to the side. 32 is divisible by 2, leaving 16. Divisible by 2, leaving 8. That's divisible by 2, leaving 4. That's divisible by 2, leaving 2. And that's divisible by 2, leaving 1. So we have a lot of pairs of 2. Let's get those paired up, and that one's by itself. But look, we created a pair of 4s here. So it's really 16 times 2. That's square root of 16, square root of 2. So back to that first term. 4 is really being multiplied by square root of 16 times square root of 2. Now we know that the square root of 16 is a perfect square, right? It comes from 4 times 4. So we could rewrite this as 4 times 4 times square root of 2. And now, since these two factors have cleared the radical, we can multiply 4 times 4 to get 16 square roots of 2. So I have just transformed 4 square roots of 32 into 16 square roots of 2. That is simplified as much as possible, so we're about to find out what do we subtract. I'll just change colors to make it easier to follow. So now we're going to work with square root of 18. 18 is even, so I'll divide by 2. That leaves 9. Divide by 3, that leaves 3. Divide by 3 again, that leaves 1. So we have 2 by itself and a pair of 3's that would make 9. Square root of 2 times square root of 9. So what we're subtracting is square root of 9 times square root of 2. When we simplify, the square root of 9, remember, is 3, but 2 will need to remain under that square root. So for this last line, 3 square roots of 2 is simplified as much as possible. So we know we're going to be subtracting 3 square roots of 2. Now we're ready to work on the very last piece here. Positive 2 times square root of 128. So we'll start with 128 and divide that by 2, and we'll get 64. Divide again by 2, and we'll have 32. Divided by 2 is 16. Divided by 2 leaves 8. Divided by 2 leaves 4. Divided by 2 leaves 2. Finally, divided by 2 leaves us 1. So a pair of 2's to get 4. Another pair of 2's to get 4. Another pair of 2's to have 4. And 2 by itself. If we have any more pairs of the same number, then we create a larger perfect square. That's 16, but we're going to leave 4, and we'll leave 2. So we have square root of 16 times square root of 4 times square root of 2. So we are adding 2 times square root 16 times square root 4 times square root of 2. So what we're adding is 2 multiplied by 4 multiplied by 2 multiplied by square root of 2. Do you see where this 4 and 2 came from? Square root of 16 clears as 4, square root of 4 cleared as 2. So what we're adding for the last term, multiply all of the terms that have cleared the radical. 2 times 4 make 8, times 2 would be 16, and 2 remains under the radical. So hopefully what you notice is each one of these terms now has the square root of 2 for its radicand. That means we have like terms. Now we're ready to take the coefficients that have cleared the radicals, and the first one is 16 minus 3, and then plus 16, and common radicand is square root of 2, so that is multiplied by the square root of 2. Now we have 16 minus 3 plus 16, that would be 29 square roots of 2. In example 3, we have 3 different terms that we're going to be either adding or subtracting. So we'll just pay attention to whether plus or minus is given in the expression. So starting with 4. Well, square root of 4, we probably know that's 2. With x to the 7th, y to the 5th, this is where we're going to use our special division of the index to know what remains and what clears the radical. So 7 is divided by index of 2, which is 3 remainder 1. So 3 bases of x clear the radical, but 1 base of x remains under the radical. We'll do the same with our bases of y. 5 is divided by 2. That leaves 2 remainder 1. So 2 bases of y clear, but 1 base of y remains. Now working with our middle term, positive 9x squared has already cleared the radical, so I'm just going to copy that portion. Under the radical, we don't have any numerical coefficients, so we can go straight to division of the index. 3 divided by 2 is 1 remainder 1. So that means one more base of x clears and one base of x remains. 5 divided by the index of 2 gives us 2 remainder 1. So 2 bases of y clear, 1 base of y remains. For that last term, minus 5xy has already cleared, so we keep that portion. And now use division of the index. 5 divided by 2 is 2 remainder 1. So 2 bases of x clear, 1 base of x remains. Finally, 3 divided by 2 would be 1 remainder 1. So 1 base of y clears and 1 base of y remains under the radical. So we want to find all the terms that have cleared the radical. 2x cubed, there's a y squared, 9x squared and another x, y squared, and last minus 5xy multiplied by another x squared and multiplied by another y. So the first term, all the terms that have cleared, that would be 2x cubed y squared. We have addition. 9 is the only number that has cleared. But x squared times x, that would make x cubed, and then y squared. Last we have subtraction. 5 is the only number. X multiplied by x squared, that would be x cubed. And y multiplied by another y makes y squared. Now do you notice that all of 3 of these terms have a common variable? X cubed y squared, x cubed y squared, x cubed y squared. That means these are like terms. And they are all being multiplied by our common radicand, which happens to be xy. See how xy remains in that first term? Xy remains for the middle, and xy remains again for that last term. So the square root of xy is the common radicand for all 3 terms. So our final step is to combine these terms in parentheses. 2 plus 9 make 11, minus 5 would be 6. The common variable portion is x cubed y squared. Common radicand to multiply by is square root of xy. So for this particular example, all 3 of the original terms ended up having a common radicand and common variables outside of the radical that cleared. But that won't always be the case. In our final example today, we have 2 square roots of 50 minus 3 square roots of 125 plus the square root of 98. So we're just working with numbers on this one. So we're starting with 50, and we'll divide by prime numbers. Since it ends with a 0, I'll start with 5. 50 divided by 5 gives us 10. You could have started by dividing with 2. The order that you divide by doesn't really matter. Let's see, 10 is divisible by 5. That leaves 2. 2 is divisible by 2, leaving 1. So we have a pair of 5s. So we know that 25 times 2 is the same as 50, and 25 and 2 are both under the radical. So our first term will become 2 times square root 25 times square root of 2. This means 2 is really being multiplied by 5 multiplied by square root of 2. 2 times 5 would be 10 square roots of 2. So our first term now is 10 square roots of 2. Let's work with 125. This number also ends with a 5, so I'll start by dividing by 5. 5 goes into 12 twice with 2 left over. 5 goes into 25 5 times. Dividing 25 by 5, I have 5. Dividing 5 by 5, we have 1. So although we end up with 3 identical terms, remember we're doing square root, so we only want pairs. this becomes 25 times 5. In other words, square root 25 times square root 5. So in the middle, you notice we have minus 3. So we're subtracting 3 times square root 25 times square root 5. That means 3 is now multiplied by 5 multiplied by square root of 5. So the middle term now becomes negative 15 square roots of 5. Do you notice how these first two terms do not have a common radicand? So we are never going to be able to combine those in their radical form. Let's go to the last term. We've got 98 under the radical. That's divisible by 2, leaving 49. That's divisible by 7, leaving 7. 7 is divisible by 7, leaving 1. So here we have 2. Here's a pair of 7s. That's 49. Square root of 2 times square root of 49. So our last term is being added. I like starting with the perfect square first. So I'm going to write square root 49 times square root of 2. So what we're really adding is 7 square roots of 2. So I'll just tack that onto the last piece. Hopefully what you recognize here now is actually the first term, 10 square roots of 2, and positive 7 square roots of 2. Those terms have a common radicand, so those two terms can be combined. So if we combine these terms, we have 10 plus 7 times square root of 2, and then I'll just include minus 15 square roots of 5 at the end. So how many square roots of 2 do we have? Looks like 17. 17 square roots of 2 minus 15 square roots of 5. And since those terms do not have a common radicand, that's as much as we're going to simplify because we want to keep these terms in their radical form. We're not concerned about what decimal equivalents these are at this point. So this would be our final answer.